Hello, everyone. This is Spencer from Hydromantis, and I'm glad you could join us for our GPSX webinar today. Today, we're going to be talking about modeling wet weather flow management strategies using GPSX. So we're specifically going to be looking at running some demonstrations and talking about various ways that you can analyze options for dealing with high flows coming through your wastewater treatment plant. So as GPSX is a process simulator, we're going to be focusing, of course, mostly on the biological part of all of this. So what kind of effects is the high flows going to have on your biology going on in the activated sludge? So we're not really going to be talking today about, fundamental hydraulics, more so just about what happens when you push a lot of water through and potentially wash out some of your biomass. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm glad that you could join me today. So as usual, I'll just review a little bit here about how to run the webinar in GoToWebinar. So you have your dashboard there, and down, for me anyway, it's down near the bottom. There's an option for questions. So if you pop out that panel, you can type out whatever questions you like in the questions box. And I'll be seeing those as they come here to me. And what we do is I'll go through my presentation and my demonstration today. And when we get to the end, I will answer at least a few of them. I think today's webinar is going to be a little longer than normal. So we'll see how long that goes. And then I'll stick around and answer a few. And then usually we try and follow up all the ones that we can follow up with afterwards if we don't get to your question. Okay, so the plan for today, I can move my slide along there. Yeah, my plan for today is to talk about various wet weather operational strategies. And of course, there are a lot of those, and we're going to narrow it down to a few of them that we're going to specifically analyze with running simulation studies. And I wanted to be able to bring in the concept of doing analysis and optimization using our tools. So we're going to look at why that is a sort of a useful way to tackle this particular problem. We're going to run some wet weather events through a particular plant that we're going to study today. And we're going to look at how to analyze three different options for dealing with that high flow. One, bypassing the activated sludge portion of the plant, talking about step feeding the plug flow part of the activated sludge tank, and also doing some storage of the storm surge and then feeding that back into the system later on. And I'm going to, at the end of the webinar, talk about how we can use the GPSX sensitivity analyzer and process optimizer tools to tackle that and try to find out, really sort of dig into the details about what would be the best way to do this. Now, as it turns out, as myself and my colleagues were preparing this webinar over the past few days, it turns out that some of these examples we have are really interesting, and I've realized now we probably should have done this as 2 or 3 different webinars. There's so much that we could potentially talk about here. So I had to make some simplifications along the way, and I'll point those out as we go. I hope we have the opportunity to come back and talk a bit more about this at a future webinar. So we'll wind things up with the usual conclusions, and then I'll stick around, as I mentioned, to answer any questions that you have. Okay, so when we're talking about wet weather challenges, those wet weather events can push a lot of flow through your treatment system. And so that can cause a range of different problems with high loading or with at least a high amount of flow coming in that may have a high concentration or low concentration if things are somewhat diluted. Obviously, the number one worry for most people is that the high flow is going to wash out the biomass that you've spent so long, cultivating and doing its job there. If you have some limited clarifier capacity, you may lose biomass in your effluent. It may indeed also really, that high flow and things moving through the plant really kind of shorten down your residence time. So you may find that if you have a sustained period of a high flow, you may find that you have trouble keeping up the SRT that you need to do nitrification or BioP or whatever it is that you're doing at your plant. A lot of places where there's going to be a high flow and potentially, a high load come into that system, that can also make for challenging oxygen supply. So you may find that there's a lot of aeration requirements coming in with that higher load, and you know, your DO control system wants to push more air in there, and so you may find that the high flow is presenting the more loading than you can supply the air for, and so that can be a big challenge there as well. And if you do lose your biomass, or there is something that's happened and there's a loss of performance, you may find, of course, that it takes a while to grow back all that biomass, depending on what kind of system you have and what kind of biomass makeup you have in your activated sludge. You may find that that could take quite some time, you know, days or weeks. So there are a few strategies for managing transient higher than normal flows. By transient, I mean dynamic, something where the flow is kind of following its daily diurnal pattern, and then it goes up to 2 or 3 or 10 times the flow for a short or maybe a long period of time, and then comes back down again. So transient meaning something where it changes and then it kind of returns eventually back to what you started with. So one option, as we mentioned, is to bypass around the activated sludge process. So this is sort of obviously taking the flow, or at least some of that flow, and then in the example I'm going to show you, after it's been through the primary clarifiers, pushing it around to the effluent. The idea there is we can at least take some of that flow. We will protect our biomass by not washing them out that way. There's options for storm surge storage, and then slow feedback of that stored water back in through the system once the wet weather event has happened. So that's, you know, can either be done in the plant, or, I mean, in essence, that's the CSO approach. But I have been to a few plants and seen a few places where they have, you know, an old sludge storage tank, or maybe an older clarifier that's not part of their regular system, and they have the ability to at least put some flow over there. And then just let it sit while the storm's happening, and then feed that back. So it saves them a little bit of, you know, immediacy of having that flow coming through. Excuse me. There's also, of course, step feeding of the plug flow activated sludge. So that's a case where you're going to push some of the flow towards the back end of your activated sludge plant. So not all of the biomass is going to see that higher flow rate. So again, it's about you know, potentially protecting your biomass, not washing it out, because some of the flow is going to see less of the activated sludge process than others. So there's also things that you can do. You may want to reduce your co-thickening. You may have special high rate treatment processes like an active flow system. And there's the image of the object that we use in GPSX to model that. And CSO operation I mentioned before, sort of storing that or managing the flow coming to the plant. That's a bit outside the plant boundary fences there. So those are lots of options, and I could probably make a whole workshop, a full day workshop out of that if we had the time. But for today, we're going to focus just on these three: bypassing, storage, and step feeding. So these are three things that we're going to take a look at in more detail: how you set those up, what happens when you run simulations, good ways to sort of analyze and understand the output that comes out of your GPSX model when you're doing these. And then for two of them, for the step feeding and the bypassing, we are going to use some of our advanced tools on those and see what we can learn from that. All right, so simulation is actually a really great way to study wet weather strategies, because you get to basically relive that wet weather event over and over again and rerun it as much as needed in a very deterministic kind of way. If you want, you can get exactly that same storm over and over again. While adjusting your operational approach, seeing what works, what doesn't, doing analysis, doing optimization, that sort of thing. You need basically three things to do this kind of study. You need a dynamic event, so changes in your influent flow and concentrations, potentially, if you like, some sort of way of making that change during a dynamic simulation that you're running in GPSX. You need some sort of operational flexibility. This is the thing that you want to test out. So that's your bypass settings, your step feeding settings, and so on. Things that you want to be able to analyze and play around with. And then lastly, a measurement of some sort of success. Like it's maybe not totally obvious when you first set out to do this. What is it that I want to look at? I mean, obviously it's going to be effluent quality, but in what way? You've got 5 or 6 different parameters. You know, some will be affected more than others. And how do you measure in a sort of very quantitative way how successful your one approach is versus another approach, because you're going to be looking at the length of a dynamic simulation. So we've done a couple of experiments here and just sort of little desktop demonstrations where we've looked at the total mass of something, like the total mass of ammonia that comes out the back end of the plant, as a nice way to do that. So I'll show you how I did that and what kind of results and things that you can learn from that. Right. Okay. So let's talk about some of those in a little more detail. So when you're doing this kind of thing, you need to set up a dynamic wet weather event in your influent. So there's a couple of different ways that can be done. But what most people do is you put the relevant inputs for that you're going to be able to change over time while the dynamics are running, and then set up a spreadsheet that will read those numbers over time. So basically, when you set those up, drag those parameters up onto a file input controller when you're in simulation mode, and then set those to file input. So over here, you'll see that when you do that, you have options to set some files up here, and you can create those. What I think most people do, and what I prefer to do, is to actually just set it all up in one single spreadsheet like this. So you can actually right-click on this panel over here once you've dragged everything there to get a copy of all of these names that you need, and just paste those right in, and then paste your columns of data that come after that. So this is actually sort of just regular standard GPSX dynamic simulation usage. And for those who are maybe new to the software, this is tutorial 6. If you open up the GPSX help menu and go to manuals and open the tutorial, go to tutorial 6, that'll tell you exactly how to do all of this. So what will happen then is when you run your simulation, it will move along and it will adjust those parameters, and you will see those things changing over time. And then you are able to make changes to things like your total flow and your ammonia and pH and temperature and anything else that you feel is something that you want to include in the dynamics of your plant. And then, of course, GPSX is a dynamic simulator. So the whole rest of the plant is going to respond to the changing mass balance of everything that's coming into the system. So there's a lot moving, a lot of, basically the whole plant becomes moving parts at that point. And then you can start plotting some of the output to see what happens to your system while that's going on. So the next thing you need to do is also have a handle on the operational parameters that you want to study. So again, drag those up onto the inputs. You can organize that in whatever way you like. So for example, I could take this setting over here. That is for the bypassing that I'm going to be showing you here in a few moments. That was a pumped flow rate on the one side of the control splitter. And I wanted to be able to play with that number. So the best place is, of course, drag that up onto a slider. And then once it's there, you can use that slider, type the numbers in, or as you'll see later on, we can put it and make it part of a sensitivity analysis or an optimization as well. So again, standard GPSX usage, but I find it's good to sort of have several tabs up here to kind of break down all of your information. Even though that's not what I'm showing here, most frequently, I do put all the influent stuff together on one tab and all of the controllers and other things on other tabs, just to keep things so that you don't have too many things taking up a lot of real estate at the top part of your screen. Okay, so that's the first two steps. The third step was a way to sort of monitor the things that you want to pay attention to that are going to be the information you're getting out of the model that'll help you decide what if what you're doing could be better. Like, so you're going to monitor your effluent quality, obviously. You're going to want to plot things like the concentrations in the effluent over time. So for the base case demonstration that we're going to be doing here today, this is what the effluent quality looks like. So you'll see here that during this relatively sustained, challenging event here, we can see the effluent TSS starts around 10, and then it goes up for a period of time, and then it kind of comes down and bounces around a bit. So these are, typical things that you would probably want to plot. And the effluent ammonia is like really great. It's fully nitrifying, and it's not for a while, and then it is again, and there's a couple peaks along the way. So these are the types of things that you want to keep an eye on in terms of understanding what's happening at your plant. Am I losing nitrification? Am I losing my BIOP? What are the things going on in the effluent? So that's pretty standard stuff. The other thing that you might want to do is to look at a nice quantitative measurement of how everything went for the total run. Like, for example, if I go back and look at that slide, if I said, how did I do in my effluent ammonia? Well, it was pretty good for probably about 70% of the run, but 30% of it was not great. So I want to be able to sort of quantify like whether this is better than some other run where, you know, this is like lower, but maybe it's higher over here or something. So I need a way to sort of quantify the results of the entire 15 days of simulation. So what I often do in that case is to calculate the total mass of the ammonia that left the plant in the effluent. So, and there's a nice way to do this. So you can use our define function, which is the red FX button at the top. So you're in modeling mode at this point and you're creating some new variables you want to plot. And I do a mass flow. And you can do this actually on any concentration that you want. So in the examples that I've been showing here, or will be showing here, I've been doing it on effluent ammonia and effluent TSS. So you go to the mass menu, you navigate your way to the effluent, and you click off effluent ammonia and effluent TSS. What you get out of that is a new defined variable that is the mass flow and multiplies the concentration times the flow. And what you get then is grams of ammonia over time. So grams of ammonia per day rather than a concentration. It is now a mass flow. So then the second step is to go back to the define function and do a totalizer on that. Now, a totalizer is basically just integrating something over time. It is calculating the area under the curve, so to speak. So what that does is it integrates your mass per time over time, and then you get mass. So that first step is going to give you a mass flow, and then the second step is going to integrate that mass flow. And what you will end up with at the end is just mass. So that'll tell you the full mass of all of the effluent ammonia that happened over that 15 days run. Now, of course, that means it is relevant to the length of your run. If you run a longer run, your mass will be more because more came out the back end of the plant. So if you're doing comparisons, you got to make sure you're running the same length of simulation each time. But I really like this as a way to sort of look at the mass loading to your effluent receiving body of water. So this is very quantitative. It calculates it every single time you do a run, and you can compare one thing versus another thing. You can still look at all those other graphs that I had there earlier, but now you've got a nice way to stick a number on it, right? So I'm going to be using this number to help drive our sensitivity analysis and our optimization later on. Okay, so let's get to the point where we're going to talk about some actual simulations here. So I'm going to run a couple of sort of a base case scenario here. We're going to show this wet weather event. And I just want to show this graph before we get started here. This is actually the sort of steady state condition of the plant before the simulation starts. The influent flow is actually 200 MLD. Now, in this particular case, this is not looking like what you might call your regular sort of intense storm, right? You know, I could have, say, for example, run a few days of normal behavior and then a really high peak and then back to normal again. And that would be sort of a 6-hour storm or something like that. We found it actually, it made a little bit easier to explain what's going on in this webinar if we made it a big, long, sustained event. So we wanted to have some dynamics in it. So you can see here that this is, it goes from the average up to 2 times. The peak is 2 times the average. I know that a lot of storm events, it might get up to like 6 or 8 or 10 for really short periods of time. This is a 2 times event where the influent flow peaks up and stays there for a couple of days, and then there's a break, and then there's some more rain, and then it goes back down again. So imagine this being sort of like a long, sustained couple of days storm, and that's what we're going to study today. Okay, so I want to just start with running a wet weather event, just to sort of get the baseline of what we're doing here. Okay, so I've got my correct version here open, and so this is the plant that we have. Influent flow through the primaries, and there's secondaries, and we're not really looking at the details of the solvents handling system here. There is a DO controller that we're controlling with this airflow over here. For those of you who may care, this is actually very similar to the setup. I based it off of some of the layouts that we've done for comparing different types of DO control systems. That was in a webinar that I did about 6 months ago. So it's very much this the same plant with some modifications. Okay, so just to show you what's going on here, I'm going to hit start. We're going to run a 15-day simulation, so that's already been built in here. And we can see that we have dragged total COD, phosphorus, ammonia, and flow up onto these graphs. So just to illustrate, we're running a wet weather event. You can see, obviously, that the spreadsheet that I'm using in the background is reading all of those data points in. So every 15 minutes, it reads some new numbers in, and those are going up and down over time. And there's going to be around day 3 here, the beginning of a sustained higher flow rate for a couple of days, and then it's going to come back down again. So as with anything in GPSX, you can poke around and look at all sorts of different outputs and so on. And here I'm just plotting the effluent ammonia and the effluent TSS. And so these are some of the graphs that I was showing you earlier. So you can see here that obviously it's responding to the changes in the influent flow over time. Okay, so this is just the thing that you want to be able to do in order to sort of set up the beginning of your study. So what kind of storm you use is totally up to you. We've done lots of different types of flow patterns as storm for various studies that we've done. For a lot of our SimuWorks projects where we're building training simulators for actual wastewater treatment plants, the plants themselves have been able to give us very detailed flow during a 2 or 3 day or 6 day period that we can actually use. So I've had some really interesting projects where we've been able to recreate an actual storm that the users have lived through, and then let them take a second crack at it or a third or fourth crack at it, and then have some time to play around and see what would have worked or what did work and what didn't work and that sort of thing. So you can use data that you've made up, or you can use real data as needed. Okay, so that's just a demonstration of running a dynamic event. Okay, move again, here we go. Okay, so now we're gonna move on to the first of our 3 wet weather process options. So this is setting up a bypass. So the object that you should use in GPSX is the control splitter. So if you go to the panel where all the flow splitting and combiners are and slide down to the bottom, it's the bottom one, looks like this. And this is set up, and it's sort of a useful tool to do a number of different things, but it is sort of the standard approach for doing a bypass. And it may seem actually counterintuitive the way I'm going to explain it, but the way that you do it is you set it up so that the pump side goes to the rest of the plant, and the other side that is not the pump side is the bypass. So what you're doing in this case is you're saying, I'm going to set this threshold at whatever flow rate you want to set. So if you open up the menu, and you'll see the pump flow setting here is 500 MLD, for example. What that means is the flow that's going this way is, if it's less than 500 MLD, all of the flow will go through the pumped side. So by default, it's set up that way to work that way by default. So when it comes, anything 500 or less comes and it all goes through that side. When the flow coming in is higher than whatever threshold you've set, the rest of it goes the other way. So 500 will still continue to come through and go to the bioreactor side, and all of the rest of the flow, and this is updated and calculated on a dynamic fashion. So the amount that's being bypassed is actually going to go up and down as the input into this bypass changes. So that's sort of the easiest way, I think, to sort of set it up, and that's the way it is in our examples. You may find that if you're modeling very specifically a plant that does it different than this, you may have to flip it the other way around, for example. But I think this is the way that most people would I've seen most people use it. So just to reiterate here, in this plant that I was showing you earlier, here's where we're setting the bypass threshold. So that means up to and including that amount will go into the bioreactors. Anything above that will go the other way around. So I know for whatever value I'm setting on a continuous basis, it will be dynamic up until it hits that threshold, and then it caps it at that amount. Everything else goes the other way. Okay, so I'm going to go back to the layout that I was just showing you. And I'm just going to note here, this is the bypass flow rate. It's actually from this menu right here. So, and we can see this amount. So I dragged that controller, put it up here. And so if I wanted to test and see what was going on, I could, for example, plot some flows and make some changes. If I wanted to run with a lower threshold, so that means I'm going to bypass more, I could make a change here. Let's actually make it 350. And so now that means I may be bypassing some because there's certain periods of time where this influent flow, so it's starting out here around 200. It eventually gets up to about 450 or 460 or something like that. That is going to have periods of time when it is going to bypass. So let's go back over here, and what we'll see in this particular case, there's not really all that much to see other than our results are looking a little different now because now we're shaved off that peak a little bit, right? And that's all automatically happening in the background. So by the way, I should mention, there's the two values that I was mentioning earlier as our assessment of our metric of success, so to speak, where we have done the mass flow of ammonia in TSS, and then we did the signal integration, which is doing the totalizer on that. And actually, when you do that process, I forgot to mention when I was on the slide, when you do that process, you will find out that it comes to our default mass units when you get to the end, which are grams. So one thing I always highly suggest is go through that process I showed you earlier. When you get to the end, switch to grams to tons or something else, because it's going to be a big number. You don't want to have to plot, 11 billion grams. So flip it over to tons. I'm showing the metric ton version here. So you can see that these numbers are increasing based on wherever we're at down here. So, and so these are concentrations. They've been multiplied by the flow at that time and then integrated as we move along. Okay, so that's basically how you would set this up and how you would control that. And now if I wanted to perform an interesting study on that, I would then try different flow bypass thresholds. Maybe it's going to be something that is different, for different reasons. If I'm trying to focus specifically just on solids, maybe there's a good number there. Maybe if I have to do something different, if I'm trying to protect my nutrient removal process, those sorts of things. Right. Okay, so I'm going to pop back to the slides and show you a comparison that I did earlier on. And in this case, what we're looking at is that we have in the black line here what it looked like under the base case. So no bypassing. That was the first simulation I ran. And then another simulation where I ran it with the bypass flow at 325 MLD. So, so we got two different amounts in our effluent, and we got two different patterns for the way that this works. So I think the most intuitive one to look at this point is how our effluent ammonia broke down. So you can see the red, which is with the bypass, it actually peaks a little bit less and it actually recovers more quickly. It happens sooner in the simulation. Now, of course, there's some other fluctuations happening down here as the dynamics were coming along. And then once we get down to this level, well, at this part of the simulation, there's no bypass happening. That's why the two lines plot right on top of each other. So this is a really nice way that you could do a comparison. You run it with, without, try different levels, do it under different influent loadings or maybe even different storm studies, that sort of thing. So that's an example of the kind of investigation that you can run. Okay, so I'm going to move on, and now we'll talk about the second of our three items, which is step feeding. Now, step feeding is the idea that you're going to push a little bit of flow farther down your bioreactor. And the way that you find that particular parameter, it's at the very bottom of the operational menu. It's where you direct the incoming flow into the various zones. So down here, you click on the little square button there, and you'll see that you get this menu now. So by default, by the way, this is going to come up with fractions, and it's going to be 1000. I always find it much easier to see it as a percentage. So you just click right here, and that'll flip over to percent. And what you can do then is you can specify how that is going to be distributed. I will note, by the way, there's one for the influent, and there's also one for the RAS coming back. So anything that's connected into the recycle connection point. which is right here, the recycle connection point, you can distribute it to down zones just the way you can with the influent, which is the upper one. So by default, it's going to look like this. All of the influent flow is going to come into the front reactor and then flow downstream accordingly. What you can then do is I could change that, for example, and split it up and make it so that it is 25% into each of these, for example. You may, what this does is it opens the door for you to investigate, many different ways of dividing up that flow and then taking a look at what is happening. So, so what we can do is I can run a simulation where we've done that. Okay, let's see here. Okay, so this is a different layout. Excuse me. And in this case, there's no bypassing. So it's the same kind of setup, the same influent, everything else. But in this case, there's no bypassing flow. So all of everything that's happening is actually built inside this object. So we'll see here if I open this up and then I scroll down here, go to influent flow distribution. As I mentioned, I find this easier to look at when it says percentage. So I do that. And then now these values could be changed. So let's go over here. And I know this will be sort of pretty much exactly the same thing that I was just showing you before, except we're changing something different. Here's all my influence stuff being read in just like it was on the other layout. And what I did was I actually opened up that menu and I dragged some of these parameters over here. And I could choose to set those to some other values other than the default 100% 000. Now, one thing that I should mention when you're dealing with these step feeding fractions is if you're going to investigate a couple of different scenarios, one thing you need to keep in mind is this all needs to add up to 100%. So I should actually have this set to percentages, by the way, just in case you need to know where to do that. You hit the gear button, put this on. Okay, so when you're doing that, you're going to be setting these to percentages. You need to make sure that you're going to make these always add up to 100%, or you're going to get some error messages popping up. So just to keep that in mind. Of course, that makes sense. You don't want to be obviously distributing more flow than you actually have coming in. So that's relatively, I think, straightforward. I'm going to move on here because I realize I've been getting a little bit behind my schedule of what I want to talk about. So so we did, again, just like that previous one, I ran a couple of different examples. So here's that base case again. And in this case, so no no bypassing this time. We're talking about step feeding. It's all 100% 000. And now if I run a second simulation, it's 25% all the way through. So now we can take a look at doing this in a bit of an interesting way. So a couple of things are going on here. You can see here that it does actually shave down this effluent ammonia peak by quite a bit during that couple of days of really sustained flow, but it doesn't perform quite as well during this other part over here. So over here, this is much lower flow. Now, in reality, you probably wouldn't be step feeding during these other periods of time. So there's like a whole other layer of optimization you could apply using this methodology. Maybe you would run the simulation under 100,000 up until this point, and then as that huge flow starts to hit, then we start doing the step feeding and then run it through this part, and then maybe you could run some simulations and optimizations to find out when you might want to jump back again, and then the rest of this could be run under the other one. So it's a nice way to sort of do that. I was going to try and actually explain that through several simulations, and suddenly that was becoming its own webinar unto itself. So, so this is really interesting to sort of illustrate if you kept it at 25, 25, 25 all the way through, but it'll be, obviously not performing nearly as well under the regularly or low loaded conditions. Because a lot of that ammonia is just going to the back end and out before, and it doesn't get a chance to get exposed to the activated sludge nearly as much. So there's a multi-dimensional optimization to be had here. Not only how do we set these four numbers up, but when do we do it? When do we start? And maybe there's a transition period. All of that kind of stuff is the kind of things that it's really fun to be able to experiment with this sort of a thing. Exactly the same storm every time, slightly different improvements on our approach to dealing with the wet weather. Okay, so now moving on to the third option for dealing with wet weather. So there's storage and pumping back. So that's basically storing over to a surge tank or an extra clarifier that you have. I was working on a project last year where they had a quote unquote extra tank that they used for this exact purpose. You can use a regular CSTR or a clarifier or an equalization tank, or pump station actually could even service as that. The pump station is like an EQ tank, but it has a little bit of high-low level control that you could automatically take advantage of. Whatever works for you. So in this case, here's an image of this system. Basically, again, that same plant, but now we've added the ability to split off some flow above a certain amount into that EQ tank, and then pump that back over a period of time. Now, doing that is now already several operational parameters that you would have to think about. So how much do we push over here? How much do we pump back? At what time? At what rate? So it becomes a quite a bit more complex problem, and it's kind of an interesting problem to think about in time, as opposed to just setting a bypass and letting the whole thing run for 15 days. So in this case, it's an interesting experiment to play around with, run the simulation for a period of time, excuse me, and then be able to sort of jump in and say, okay, at this point, I want to do something. Let me get to my example here. Okay, so what we have here is this tank setup. My colleague Dan, who helped set this up for me, also used an EQ flow controller here. What that is actually doing is automating the process of sending the flow back so that we don't have to manually stop it, change a pump rate, continue, et cetera, et cetera. That's actually just going to come to life on the 7th day all by itself and at a specified flow rate. So anyway, let's run a simulation here just to see what that looks like. So in this case, actually, I have a scenario set up that I want to use here. So now, of course, there's lots of other considerations here. We have to make sure that we have a big enough equalization tank to actually be able to store it all so you don't end up with overflow going to your effluent, for example. So this is going to run for a little bit here. And let's see, here's our EQ tank. So right now, the EQ tank starts empty. I do recommend that, by the way, as a sort of a way to keep things straight in your mind when you have this. Of course, in most places, if you do have a place you want to store some extra flow, you're going to want to have that empty as much as possible. So if you go to, I realize I jumped really quickly to that menu, in initial conditions and initial volume. So what you're doing here is you're going to turn this off. This is by default on for all of our tanks. So when you drop a tank on the screen, it's going to assume it's full to start with. So turn that off, and then that will allow you to enter an initial reactor volume and set that to 0. So when the simulation runs, it's going to start with an empty tank that you can then start adding some volume to. Okay, so let's go look at our effluent quality. Basically, this part is exactly the same at where we're at right now. So I've got it set so that anytime it goes above 350 MLD in terms of the flow coming to the bioreactor, that it is going to split some of that flow off and put it in the EQ tank instead. So let's look at the EQ tank volume. So right now, for that first part of the simulation, it was empty. And then it had some flow pump to it, and then a little bit of a flat spot, and then a whole lot as that big flow, sustained flow hit. And so eventually, at some point, this thing is going to get to the point where we've stored the excess flow, and it's going to drop down below 350, or sort of our threshold again. And right now, nothing is being added to it, so it's just sitting there, partly full, waiting for the storm to end, and then it can be pumped back. Oh, no, we had a little blip there, a little bit more was added to it. And then we've chosen a particular pump rate back here again, and that could be part of your analysis and optimization is when do we want to feed it back and how quickly. So by default, we've set it up so that I believe it's day 7 or 8, it starts pumping back. And we should see that here. Once that's, I think we're pretty close to the end of our sustained event here. And then suddenly this will start pumping back into the system. So there it goes. And so that's controlled by this EQ timer controller. And that's a real nice way you could set that up. And the rest of this, it's just pumped out. And then since the flow never comes back up above 350, this is going to stay empty for the rest of the run. So that's how you would set that up in GPSX. You would want to set up a tank, start with it empty, pump some flow over there under whatever conditions are appropriate for your facility, and then set something up so that it will start pumping back at a certain time. So whoops, I need to bring that back. So one of the things that we could investigate, for example, is do we want to start pumping back here, or maybe we would wait later, or maybe we could have started earlier? What's the slope of this line? Should we pump it back at a much slower rate, for example? Those are all things that could be part of your analysis. All right. Let's stop that and go back to our slides. Okay, so this will be the last of the three comparisons, side by side here, where we're showing what it looked like without doing any storage, and then once again with the storage. Now, as I mentioned earlier, lots of different ways that we could do that. This is the particular result for doing it starting at 7 days, pumping it back after we had stored flow that was over 350 MLD. So you could see here that, of course, it is kind of shaved off this part of the peak and put it down here, for example. So maybe there's better options. Maybe we came back too quickly. See, this is what you're seeing here is that this is actually right after 7 days. So maybe we came back too quickly. If we maybe pumped it back over a longer period of time, this peak wouldn't exist. So lots of fun and interesting things you can do with that. Okay, so now there's our three things that we investigated, and I showed you how you can set those up. What I then wanted to do is, rather than you sort of just personally poking around and saying, what if we do this, what if we do that? There are some formal ways that you could investigate the strategy using the tools that we have built into GPSX. So in the GPSX Pro license, you have your analyzer, which does sensitivity analysis, and your optimizer. Now, this is where that mass in the effluent number comes in, because this is a nice way to sort of put some numbers to how good our effluent looked. So what I did was I set up an effluent ammonia mass versus bypass threshold sensitivity analysis. And I just snapped a screenshot while it was running here to show you. And I want to point out a couple of things about how I set this up. First of all, I was using the Analyze tool up here. So you can see the check mark, that's the analyzer, has been turned on. And note down here in the lower right corner, this tells you what mode you are in and which of the tools you're using. I was using the phase dynamic sensitivity analysis. What that is it is taking a parameter, setting it to a certain value as part of that, and then running a dynamic simulation and collecting the results from the end of the dynamic simulation. So what that is doing is it is basically allowing me to run a 15-day simulation and then calculate and pick up that number that I wanted, that mass of everything that went out in the effluent over those 15 days. So right now we're going to collect and plot that totalized mass flow of ammonia. So what I'm doing here is I set that up so that it's doing it on influent flow. So it takes a little while to run this. I think it was about 8 or 10 minutes to do it. I did it at a fairly high resolution. I was stepping from 200 MLD up to 500 MLD in steps of 25. So I got a nice smooth curve here. And so what that told me was what is the amount of ammonia in the effluent over those 15 days versus that bypass threshold. So let me go back and show you what the slide looked like. So this is the results I got out of that. And so you're looking at that and you can see that, first of all, it jumps out right away that there is sort of an optimal point in the middle here. And we'll get there in a moment. The first thing to realize is this is bypassing too much flow on this side of the graph. So just to reiterate again, the bypass threshold is the amount at which we would start bypassing. So when you're on the left here, at these low numbers, it means we have a low tolerance, and we are going to start bypassing any flows above 200 or 260 or 300. So that means we, at the very low level, we start bypassing. And that's why this is showing that there's a high amount of ammonia in the effluent over those 15 days is because basically we're bypassing too much. We're not treating enough. Over at this end, this actually becomes a flat line after a while because now our bypass threshold is so high, we're not bypassing anything. And so it doesn't actually matter. You can make this number as big as you want, and it's always going to be the same amount of ammonia in the effluent because basically all of it went through the plant. So what we want to do is find out that spot in the middle where we bypass a little bit, but not so much that we're decreasing the quality of our effluent. And so that point is right here. Right there, it's basically 320 MLD, and oops, I located that arrow in a little bit the wrong spot there. And it was at 8.1 tons. That was comparing, by the way, to about 9 tons when you're over here, 9 point something. And so, we shaved off a ton by bypassing a little bit of the flow. So it doesn't go above 320 all that frequently, but it does during that little bit of that sustained event, not most of the rest of the event. So that's how you would sort of use our sensitivity analysis to find sort of the optimal bypass threshold to protect your nitrification. Okay, so now I've done the same thing exactly, but I've plotted in this case the effluent TSS instead of the effluent ammonia. So this was just grabbing a different graph off of the same sensitivity analysis. And you'll notice right off the bat that it looks different, actually. And in this case, it's because, of course, the flow that was pushing all of those solids out of the secondary clarifiers and out into the effluent, the more solids you bypass, it goes straight out the effluent. And so there's not, you end up with a very sharp, skinny peak of your breakthrough solids. So at any point, bypassing some of that is going to be a problem. So anything over on the left-hand side here, you're going to have very high effluent solids in your effluent. So what ended up being was that, basically 420 was the optimal point, and anything to the right of that was exactly the same number. So at 67 tons of solids. So it's interesting analysis. If you base your optimal point of bypassing on solids, it's going to give you one number. And if you base it on ammonia, it's going to give you a different number. So maybe you need to go somewhere in between. So of course, all of this is going to be driven by how you measure your effluent quality in terms of regulation. So maybe you don't have the opportunity to even bypass any significant amount of solids at all because of the way that your plant is regulated. So, but on a process-wise basis from an analysis here, you can do this really interesting sensitivity work with the GPSX analyze function. It basically runs a simulation, collects a data point, runs the next simulation, connects a data point each time, increasing that threshold, and then plots all of that together for you. Okay, so that was the analyzer. Now I want to talk about the optimizer. So the optimizer is, for those who might not know, a search routine. You give control of some parameters over to GPSX. It runs a simulation, it makes changes to those parameters, and it runs the next simulation, and so on and so on. And it does that while trying to achieve a specific objective. So in this case, excuse me. In this case, what I wanted to do was to minimize the amount of ammonia in the effluent. So again, we're going back to that mass calculation, and then we're going to say we're going to put the optimizer on that, minimize that number as much as possible. And we're going to give you control of these step feeding fractions like we were talking about earlier. Now, watching the optimizer run is actually not that interesting when you're watching the mass number. What is actually more interesting to look at is these effluent concentrations. So this thing is not what was actually being optimized. It was the total mass number, but this tells the story a little better. So what it does is it picks up these as a starting point, runs the first simulation. Then it makes a few changes and it runs it again. And so when it made that second guess, it is now at a different operating point. It's pushing some of that step feeding flow a little farther down, and it does it again and again, and it keeps finding the best set of combinations until you get to the point. So this last one that's showing here is actually the better example. This one on the top is actually the starting point, and then now we're down here. So we've improved that, and of course this area under here is really that metric that was being used. But of course, all of those things that I was saying earlier about step feeding still apply. We can see down here, we probably didn't even need to do step feeding at all here or here, but we do need to do it in the middle part. So again, we could even add on to the optimization question by saying, when do we start and when do we stop? And we can even let those be decided by the optimizer itself. And so those are all really, really interesting and very detailed questions that we could include in our optimizer problem. And again, I really wish that I could have made an entire webinar around this particular example. It turned out to be so fascinating to play with. So we will hopefully revisit that again soon. Okay, that's the end of the part I wanted to talk about, the three examples, the bypassing, the storage, and the step feeding, and then how to use those tools, the GPSX tools there. One example of the analyzer, the sensitivity, and then one example of the optimizer. So just to wind things up, and I realize I'm getting really late in my hour here, is that I wanted to talk about a few other things that I know are relevant to the question of wet weather management. So there's a few other things you may find useful. We actually have this stormwater runoff influent model that you can use, and then it takes rainfall as an input and generates different kinds of effluent flow rates. What I've seen people use is you may want to put your regular pipe that's your regular wastewater influent and then have this beside it and then combine those two flows and feed them into the plant. So what this does is when you feed it the rainfall, it basically is otherwise equal to zero. And then as soon as a rainfall event, that's these little blue rainfall events, as soon as a rainfall event happens, it pumps some water and it comes to the plant slowly over time. And here I did a bigger one, and of course it's decaying over time, and then there's a couple more rain events, and then so on. If you let it run long enough, it'll eventually return to zero. The length of how long it takes to drain the watershed and get all that flow to the plant is a function of these other parameters here, such as your catchment area and all these sorts of things. So, so this is an interesting little tool that you might find helpful. And in fact, we used it as an example in some of our Python examples that we have. If you're really into writing your own custom code, you can use Python to generate the storm using all the interesting statistical packages that they have, and generate some hypothetical rainfall and then convert that into an influent flow with this influent object. Okay, so I wanted to go into a little bit more depth here, but we didn't end up running enough time on our webinar today, but we do have a high rate treatment process. So that is also relevant, of course, for wet weather events. This is what we call our high rate treatment system. It could be used to model the active flow system. So you're looking at adding polymer and a ballasted sand in order to be able to do some very high rate settling. And then it goes into the system and is clarified out and returns the sand back around to be reused again. So we have a special model, a special object for that with a special model. The equation here being used for the solids capture, there's quite a few different options in there. And if you open up the GPSX technical reference, you can find all the details you need to know about using this. So we've used it on several projects over the years. And lastly, I will mention too that there's all sorts of other types of controls that you could build into your system that are based on the regular controllers that we have, like the PID control loop and the timer and the on-off controllers and so on. All of that is available, and we talked about in quite a bit of detail back last fall in our Implementing Advanced Process Control webinar that we did about 6 months ago. So I recommend, if you want to look at high flow events, looking at ways that you can implement things that will automatically come to life and do what they're supposed to do, you can take a look at this webinar as well. Okay, so to sum up all of that, basically, the wastewater treatment plants see really complex dynamic behavior in those systems when a wet weather event goes through them. There's obviously a lot of stress on the system as the load is increased, but even dropping off the load really quickly can do a lot of dynamic things happening in that system as well. So what we'd like to be able to do with a simulator is to analyze that same wet weather event over and over and over again and refine the approach and learn about what that is supposed to be able to do, and use things like the analyzer and optimizer tools in GPSX to be able to help find that optimized type of approach.